So today morning I was recording a very important video for all of you, that is all 5 marker in one shot, that is one long marathon video where I was going to discuss 16 very important important derivations for your PU2 preparation. But something happened which I didn't expect, was that my video got recorded. As you can see, I am teaching here, but my audio didn't get recorded. So whatever I told here, that was not recorded, so you will not be able to hear me if I give you this video. So what good thing happened is that the file that I was working on is now completely ready with all the derivations, everything that I have done. So I am going to discuss the entire thing, and in the good thing is about that is the everything, the time taken for the entire video will be now very small, not a very long marathon video. That was the theme of this series, that is marathon series. So you can enjoy the series. It will be much smaller, much shorter than whatever is the original video was now. But that will help you to score well in your PU board exam. So I am going to explain the steps anyway, but I will be not writing them directly. Now in this lecture we are going to discuss, obviously I told you what was our goal is. Our goal was to score all the 5 marker directly. So let's see, we have 5 marker questions is asked in our annual exam, our PU final exam, and we need to answer 3 of them, right? So we all know that, and 15 marks is allocated for that. And if you study all the derivations that I am going to discuss in this lecture, then definitely you will scoring all the 16 marks, that all the 15 marks that is allocated here, right? And if you have studied it, does not matter. If you have not studied it, does not matter. I am going to give you 16 very important derivations and their derivations, obviously. So first derivation is derive an expression for the electric field at a point due to an infinitely long, thin, uniformly charged straight wire using Gauss law. So let us construct so first of all, there is a long straight wire, okay, charged wire. What is the meaning of long? Long means it is infinitely long. So both sides, on the top side and bottom side, it is very long, and it is given that uniformly charged. So what is the meaning of this uniformly charged? Uniformly charged means the charge density is given. Charge density is basically lambda. Okay, so charge density means charge per unit length. So if you take any unit length from this wire, the charge on that will be lambda. Okay, so lambda is basically coulomb per meter, basically, right? So the unit of lambda is coulomb per meter. And to solve this, how to approach this? First of all, you have to construct, this is the point where we are trying to find the electric field. Say this is the point P where we are trying to find the electric field. That is a distance r from the wire. Okay, so at a distance r from the wire, we are trying to find the electric field. Now what we have to do? First we have to construct an Gaussian surface such that this point P lies on the surface of this Gaussian surface. Okay, and the Gaussian surface in this case will be cylindrical, because a straight wire like this has a cylindrical symmetry. So because of that, we will construct a Gaussian surface of radius r, and length is L. In this case, length L is, we have assumed the length of the cylinder. Length is basically not given here, so be careful. We cannot keep the L at the end of the derivation. L should go out of the derivation. So first of all, we also have to understand that all the electric field lines coming from this wire actually passing through this cylindrical surface only. No electric field is passing through top and bottom. Okay, now what else? What is the total charge enclosed by this Gaussian surface? Total charge enclosed by this Gaussian surface is charge per unit length into length, right? That is the total charge enclosed by the Gaussian surface. Now from Gauss's law, we can say that E dot ds is basically Q enclosed divided by epsilon naught. So from there, again, because of the cylindrical symmetry, E will be constant throughout the surface of the cylinder. So E will be coming out of the integration, and only integration ds will be there. So that is equals to Qn by epsilon naught. That is Gauss's law. Now what is the surface area of the cylindrical surface? Cylindrical surface can be considered to be a rectangle of two surfaces, two sides. One side is, if you cut it from this side, okay, and open it, so you will get a rectangle, right? And the length of this will be 2 pi r, and breadth is L. So breadth is L and length is 2 pi r. So if you multiply them, you will get the total surface area, that is 2 pi rl. So 2 pi rl, and if you put the value of q enclosed over here, that is lambda L by epsilon naught, so L will be cancelled, so you will get E equals to 1 by 2 pi epsilon naught lambda by r. So one more important fact is that in this case, as you can see, the electric field is proportional to 1 by r. So this is a question that comes in objective questions as well, in MCQ questions as well. So for a straight wire, the electric field varies with 1 by r, not 1 by r square. Now next derivation, derive an expression for the electric field at a point on the axis of an electric dipole. Very, very common. So we have a dipole. Dipole means two charges equal and opposite, separated by a small distance. So the plus charge is kept here, negative charge is kept here. Now the dipole moment of the dipole is basically from negative to positive, that is why it is given by this arrow, and the distance between the dipole is basically 2a, and the point where we are trying to measure the electric field is P, that is at a distance r. Now in case of dipole, from where you will measure the distance? The distances are always measured from the center of the dipole, so that is why the distance is r here. Now distance from the positive charge will be r minus a, so from the positive charge it will be r minus a, and from the negative charge it will be r plus a, because in that case you have to add this extra distance. So from the negative charge it will be r plus a, from the positive charge it will be r minus a. Now what will be the direction of the positive charge? Now in case of electric field, if you have watched my numerical video, whenever you are calculating electric field, the direction of the electric field is important, the sign of the charge is not important. So we will be investing on the direction of electric field rather than the sign of the charge. So in this case, positive electric field is on the right hand side because it is always acting away from the charge. Okay, and the negative electric field will be towards the electric charge, that is always coming towards the electric field. So electric field due to negative charge is E minus, electric field due to positive charge is E plus. So from there what we have to do, you have to calculate E1 and E2, E plus and E minus, and then we have to find out which one is bigger. Based on that, the final direction of net electric field will depend. So E plus is basically kq by r minus a whole square. We already know this is distance is r minus a whole square, so that is along BP, and E minus is kq by r plus a whole square, and that is along PB. Okay, so one is along BP, one is along PB. Now which one is greater? So as you can see that because the positive charge is closer, the electric field due to the positive charge will be much higher. Okay, so the net electric field will be E plus minus E minus. So just do the mathematics step by step. kq will be common, then r plus a whole square will be on this side, r minus a whole square will be on this side, the negative sign will be in the middle, and the denominators will be multiplied. Now while multiplying the denominator, I have taken the square sign common, and whatever is left, that we have arranged and we have written it like this. Now this is a plus b whole square minus a minus b whole square. So a plus b whole square minus a minus b whole square is easy to remember. Formula is 4ab. So instead of 4ab, here it is a is r, b is a, so it is 4ra. And in the denominator, a plus b into a minus b, that is a square minus b square, and there is a whole square common, so that is coming over here. kq is common anyway. Now what we have to do, we have to reorganize it. So to reorganize it, I have done 2kr, so k into 2r I have kept it in one side, and q into 2a I have kept it in another bracket. Denominator remains the same. Now this q into 2a is basically the dipole moment of the electric dipole. This is the dipole moment of the electric dipole, that is the definition of electric dipole moment. So we have replaced this value over here, so it is k into 2r p by r square minus a square whole square. Now there is a approximation that we have to do, that the dipole, basically the definition of dipole says the distance between the charges is very small. So in that case, if the distance is very small, we can say that the actual distance of the point from where we are measuring the dipole moment, measuring the electric field, is very, very far compared to the distance A. If 2A is small, A will be much smaller, right? So R will be much greater than that of this distance A. So from there we just did the approximation. Now what is the approximation? We put this A equals to 0. Okay, so A equals to 0 means only R square, and there is a whole square. So R square whole square is R to the power 4. Now there is a R in the upside as well, so these R will cancel, one of the R will be cancelled, so we are left with R cube. So the final net is 1 by 4 pi epsilon naught. Now the time for us to put the value of K here, so 1 by 4 pi epsilon naught 2p by R cube. Now vector form, it is very, very important, the final result has to be in the vector form. So vector form, if you see that what we have got, that electric field, positive electric field was higher, right? So positive electric field was higher means it is in the same direction of that of the dipole moment. So net electric field is 1 by 4 pi epsilon naught 2p by R cube, because E net and dipole moment both are in the same direction, in this case along the positive x direction. Okay, so both are in the same direction, that is why final resultant electric field is positive. Also you have to note that electric field is basically proportional to 1 by R cube in case of the dipole. Now next is derive an expression for the electric field at a point on the equatorial plane of an electric dipole. So now what we have seen is that same case, two charges separated by a distance 2a. Okay, now we are calculating along this line, which line separates this dipole into two equal halves. Not only line, you can consider a plane as well. Along the plane, at any point on the plane, the same formula can be applicable. So but we are considering this line only for now. So along this line, if you see that electric field due to positive is away from, electric field due to negative is towards, but they are not lying on the same line. Okay, in the previous case one was along this direction, another one is in this direction, but in this case they are another one is opposite direction, but in this case they are not on the same direction. So we cannot apply the same logic. So as I said, the sign of the charge is not important, but the direction of electric field is important. So what we will do, we will divide this electric field into two components. One is along y-axis and another one is along x-axis. But before doing that, you have to remember that this triangle, this is because this is an equatorial plane line, this triangle is an isosceles triangle. That means this side is equals to this side and this angle is equals to this angle. So both angles are equal. Now you can consider this line is parallel to this line. This is the x-axis, right? This is parallel to x-axis. So they are parallel, and this is the bisector. If this is the bisector, then this angle theta means this is also theta. Alternating, this is a similar angle. And this is where we are seeing like a Z-like pattern. In case of Z-like pattern, I said this angle is equals to this angle. This is an alternating angle. So alternating angles are also equal. So both angles in this part are equal to theta. That is why whatever component you take along x-axis, they will be added cos theta. Cos theta, both electric field plus and minus will be cos theta components, and along the y-axis both will be sin theta components. So along the y-axis they will cancel, for one is in the upper direction, another one is the downward direction. So y direction cancels each other, only x direction they are getting added. So, and one more thing that we have done is we said that this E plus and E minus are same, and because they are equidistant from the point of observation, so equidistance means electric field will be, magnitude wise electric field will be same. So that plus and minus we have said that is equals to E. So and so if you add E cos theta plus E cos theta, that becomes 2E cos theta. So we are trying to find this 2E cos theta. Now what is the value of E for any of the charges? It is KQ by R square. So KQ by R square is here square root of r square plus a square, because this is r, this is a, so square root of r square plus e square, Pythagoras theorem. So from there, if you do the square of that, then square root will be gone, so only r square plus a square is left. Now we have to put this value over here, and we have to find the value of cos theta as well. What is cos theta? Cos theta is base by hypotenuse. Base is a for this angle theta, and hypotenuse is this side, r square plus a square square root. So cos theta's value we have put it here, and from there we just done r square plus a square square root of r square plus a square, so it will be r square plus a square to the power 3 by 2. And from there we will get again same approximation we will do. Approximation is r greater than a, r is very greater than a, then in that case we will put a equals to 0, and by after approximation, if you put the value of k here, we get p by r cube. So p by r cube, again what is the vector form? So dipole moment is always from negative charge to positive charge. Dipole moment is always from negative charge to positive charge, so that is in this direction, and our resultant electric field is in this direction, so they are basically opposite direction. So in vector form it will be E net equals to minus 1 by 4 pi epsilon naught p by r cube. Now if you see that magnitude wise, electric field on the axis is basically twice that of electric field on the equatorial plane, EP. This is EP. So this is also one important point to note, and both cases, both are proportional to 1 by r cube. So if you remember last derivation we did, there was a 2 over here and it was positive, and there is no 2 over here, so basically axis is stronger, equatorial plane is slightly weaker, and it is twice, basically axis is twice stronger than that of the equatorial plane. Also both of them are proportional to 1 by r cube. Now let's move on. If you are studying in KCET, then obviously you are aware that we have, if you are preparing for KCET, that is actually you already aware that we have launched Abhyas KCET test series, where you are getting 35 tests along with their detailed video solutions, all the doubt clarification, and an insight to the 5-year KCET previous year questions, one shot revision chapter wise. So everything you will get if you purchase this Abhyas test series. It is a paid course. The price is $14.98, and if you purchase it right now $14.99, you will get PU2 test series as well. Okay, absolutely almost free of cost. So PU2 test series including Abhyas KCET is $14.99. Okay, here you will get 35 total tests. Out of that, 4 are free test series. To access the free test series, you have to register in the given link below, and through Novo Parent app you can access the test series. Novo Parent app or Novo Parent website, you can access that, and it is more importantly, it is basically computer based test, so you can test it and you can check how much you have scored, what is your score, and how others are performing against you. That will also be available soon in our website. So once all of you are appearing for the tests, there will be a comprehensive list how much you can expect it to score. That will be very clear to you if you get this test series, and everything is available only for $14.99. Now let's move on to the next part. Derive the expression for electric potential at a point due to a point source charge. So point source charge is Q placed over here, and we are trying to find electric potential at some point P. Okay, and how to find the electric potential. So electric potential definition says that it is basically work done to move a unit positive test charge from infinity to a point in the electric field. That is the basic definition of electric potential. Now to do that, what we have to do, we have to take a test charge Q. This test charge started at infinity and it wants to reach at this point P. So for example, you started from Delhi, you want to reach Bangalore, you want to measure the distance, or you want to check how much it costs if you are traveling from Delhi to Bangalore, how much food you need to buy, how much it's cost. So different research experiment you can do from this route. But you started from New Delhi, the train is now stopped at some intermediate station, say Yadgir, okay, and you want to check, but you have not yet reached Bangalore, okay. So from Yadgir to Yadgir, how to calculate the potential? So for that we have to consider this is the Yadgir station, okay, point X. So this is some intermediate station which is not yet our destination and obviously not infinity. We cannot tackle infinity, that is why this is the trick that we are going to use, that we will consider some intermediate point. Train started at infinity long back, it reached to some intermediate station, and from there we will consider a small displacement dx and we will try to calculate the work done. Definition of potential is basically work done. So this is Yadgir cabin, say some intermediate station, Yadgir cabin. From here to here, how much work is done? That is a small work dx. So what is first of all, what is the force acting on this charge, test charge, when it is at x? Force acting on this charge is basically Coulomb's law, kqq by x square. That is the force acting on this charge when it is at point x, right? Now this is the external force, this is the internal force, right? So this is the internal force. Maybe it is repelling, maybe it's attractive, we do not know, but this is an external force. We are assuming this is an repulsive force. So to overcome this force and do extra work, minimum force that is required is exactly the same but in the opposite direction, right? So the external force that we have to apply is basically negative of that F. So this F is the field force due to the field. This force we are applying, this is the force that we are applying, so that must be negative of the applied force. Very, very important to remember. So the external force that we apply is minus kq by x square. Now the small work done to move this charge by this small distance delta x is basically dw is equal to f external into dx, okay. And then what you have to do, you have to separate all the this total work done is basically integration. Obviously if you have constructed dw, that means the final is integration. Now while doing the integration, it is like an application of integration, so the constant will come out of the integration and whatever is inside, that will be dx by x square, because that is the variable term. X is varying, right, with time. So dx by x square is the term. Now what is the integration? Integration is limit will be, starting point is infinity, ending point is r, so initial to final, infinity to r. So integration of 1 by x square is basically 1 by x. So minus 1 by x actually, so minus 1 by x. Now you can take this negative sign common and bring it outside, so negative will cancel, so it will become positive, and then first will be upper limit, that is 1 by r, minus the lower limit, that is 1 by infinity. Now 1 by infinity is 0, so we are left with kq by r. This is the work done. Now the potential is defined by work done by unit positive charge, that is work done per unit charge. So work done per unit charge means you have to divide it by this q. So this is the definition of potential. So work done divided by q is the potential, that is kq by r. Now just to formalize it, you have to put the quote and tie to it, that is, or tika to it. 1 by 4 pi epsilon naught q by r is the potential at this point P. Okay, so remember the steps. First we will start at infinity and then we will reach some intermediate point, that is our point of operation. Our entire operation happens here, okay. Then through integration we add the final starting point and ending point, okay. Practice at least twice, this is very, very important. Next is obtain an expression for potential energy of an electric dipole placed in a uniform electric field. Define the energy density and energy density of a charged capacitor. How the energy density related to the electric field present between the plates of a capacitor. So this is the part B. Part A, let us answer first. Part A is basically we have kept an electric dipole in an external electric field. How to calculate the potential? So first of all, when you keep this dipole in the electric field, positive charge will experience a force in the direction of electric field and the negative charge will experience a force in the opposite direction of the electric field, and the dipole moment, which is from negative to positive, will make an angle theta with the applied electric field. So because of this, there will be a torque acting on this system. So what is the expression for the torque? We already know that the torque is P cross E, right? Or scalar form is PE sin theta. Now if you want to rotate this dipole by a very small amount d theta, then again it is any potential is basically work done. Okay, how much work you have to do? The small work done dw is basically tau into d theta. In case of linear motion mechanics, you remember that the work done was force into displacement, right? We have done the same thing in the previous derivation as well. Work done is basically F into dx, right? Now in case of, this is for linear motion. For rotational motion, the same thing can be written as tau into d theta. Tau is the equivalent force in rotational motion, d theta is the equivalent displacement in rotational motion. So they are all linked. So f dx becomes tau d theta in rotational motion. So this is the work done. Now again we have constructed the equation P sin theta d theta. What do you have to do to calculate the total work done? To calculate the total work done, you have to integrate it. Now integration limit is very important in this case. We are not integrating from 0 to theta. Integration starting point is pi by 2 because at this point the potential becomes 0. We will see that. So this is the 0 potential, this is the final potential. So if you do the integration, you get minus cos theta pi by 2 to theta, so that will be minus PE cos theta. So this is the work done, and this is the work done means this is the same energy of the dipole. So U is equal to minus PE cos theta. So if you put the pi by 2 over here, you get energy to be 0. That is why we choose pi by 2 as our starting point of this integration, so that we don't encounter any integration constant. Okay, this is a small easy derivation. Practice it at least twice again to remember it. Now this is the second part. Define energy density of a charged capacitor. How is the energy density related to electric field present between the plates of the capacitor? So energy density of a charged capacitor is the energy stored per unit volume in the electric field between its plates. So U is equal to total energy stored divided by volume. Here V is volume. So this is energy density, this is energy stored, this is the volume. So this is the formula, and the relationship between the electric field and the electric energy density is U is equal to half epsilon naught into E square. Now derive an expression for the effective EMF and effective internal resistance of two cells of different EMFs and internal resistances connected in series. This is also another semi-important derivation, but this is also coming in your PU board exam, and if this comes in your PU board exam, then you should consider yourself lucky, because this is a very simple easy derivation. So we have two cells epsilon 1 and epsilon 2 with internal resistances R1 and R2 connected in series. Now we know that in series combination current remains constant, so whatever current is passing through the external resistance R, the same current will pass through the other resistors as well. Okay, now the equivalent circuit of this will be one only EMF, one only equivalent resistance, and the same current will pass through the same external resistance. Now when we are considering resistances series in parallel or capacitor series in parallel, we add one cell, but when we are considering cells in series or parallel, we add one resistance. Okay. Now applying KVL, now we have to apply KVL in this loop. Okay, so applying KVL in number 1. So this is number 1. What we get? So we have to start from somewhere, so let us start from there. We are coming over here, no resistance here. Now this is some resistance coming over here. What is the current? Current is I. What is the resistance? Resistance is R. So I into R. Now next is again some no resistance, again another resistance coming over here. So another resistance means what is the resistance? R2. What is current? I. Are we going in the direction of current while we continuing our journey? Yes, we are going in the direction of current. So direction of current means sign will be plus I into R2. Now for now we will ignore this EMF, and then we will come to the next resistance. Again same current I is passing, and it is again we are going in the direction of current. So I plus IR1 equals to now we will do whatever is this EMFs connected. So EMF 1 is connected, EMF 2 is connected, and both of them are sending current in the same direction. So epsilon 1 plus epsilon 2. Now just separate the term IR from here, and we will write epsilon 1 plus epsilon 2 minus I into R1 plus R2. This is equation number 1. Similarly, if we apply the KVL in the loop in the second circuit, that is the equivalent circuit, we get IR plus IR EQ equals to epsilon EQ. Okay, from there again we have to separate IR is equal to epsilon EQ minus IR EQ, that is epsilon EQ is equal to epsilon 1 plus epsilon 2, or R equivalent is equal to R1 plus R2. Okay, now derive an expression for one more thing. So we have find the equivalent EMF and equivalent resistance. These are the two important things that we have to find, right? Now same thing we are doing in the next question as well, but in this question we are doing it for cells in parallel, which also very common question. Almost every alternate year this question comes, but if you see this question, slightly be cautious. You have to practice it at least 3 to 4 times to get hang of this derivation. So here we have two EMFs, epsilon 1 and epsilon 2, connected in parallel, and their internal resistances R1 and R2. Okay, now in parallel combination the voltage remains same, okay, or that is IR will remain same. Now total current is IR, but the current through the first cell is I1. The same current is exiting, same current should come back because conservation of charge. Similarly, current through the second cell is I2, and same current will come back as I2 as well. Now we apply the KVL for the first loop, that is this EMF 1, number 1. So if we apply KVL in 1, we get IR plus IR1. So R is basically common, IR is through the external resistance, and are we going in the direction of current? We are going in the direction of current. What is the current? Current is I1, resistance is R1, so that is equals to only one EMF source is connected over here, so that will be epsilon 1. Okay. Now for the second part, what we get is now the second loop, that is the second loop, this is the second loop. Now through this again same logic we will apply, and we can find I1 and I2. That is our objective. So we have calculated I1 after writing this equation. So I1 and I2 you have written. Now what you have to do, you have to add them. Now from the obviously Kirchhoff's junction rule, I1 and I2 are entering, so that should be equals to total current I. So I1 plus I2 equals to total current I. That's what we have done over here. That is equals to epsilon 1 by R1 plus epsilon 2 by R2 minus IR I by 1 by R1 plus 1 by R2. So you have to practice it, and there is no way you can remember it, like how I have got this. Okay, so I1 is equal to, we have divided the R1 to both sides. So that is that depends on your practice. If you practice this derivation, you can solve it. Step is okay, steps can be remembered, but exact value you have to practice it at least 2-3 times. So we have calculated this, we are saying equation number 3. Now same thing we will apply in our equivalent circuit as well. So if you apply the same thing in your equivalent circuit, you can find the I, that will be equal to epsilon equivalent divided by R EQ minus IR by REQ. So from there you can compare this term and this term. So you see that epsilon equivalent is equal to REQ into epsilon 1 by R1 plus epsilon 2 by R2, or 1 by REQ equals to 1 by R1 plus 1 by R2. So from this comparison you get this one, from this comparison you get this one. Now you can leave the answer over here, but since REQ you have calculated, now you can put the value over here, and this will be the final answer. Okay. Now next is arrive at the balanced condition of a Wheatstone bridge using Kirchhoff's current rules. Okay, now you have to remember that this is we were expecting this derivation for last 2 years, but it didn't came. So maybe it will come, maybe it will not come. So you have to be prepared. Maybe cells in parallel will come. So that is why I did all the derivation possible from this chapter. Arrive at the balance condition. So what we will do? We have Wheatstone bridge, which is basically like a square having 4 corners. So this is a structure of Wheatstone bridge. There is a galvanometer connected over here. Okay, now they have told you to find the condition of balance. So to do that, what you have to do, you have to assume that the current is through this is I1, current through this is I2. Now this current I1, after reaching over here, there is a 2 path. Say we are saying that the current through the galvanometer is Ig, and current through this will be I1 minus Ig. Ig is already left, I1. Now here at this junction, Ig is coming from here, I2 is coming from here, they are merging, so the exit current is I2 plus Ig. Right? So this is the basic structure that you have to remember. The entire thing was done. Now it is slightly, because I have done it past also, that is why it's slightly messy. So that is why I explained it to you with this simple diagram. There are resistances, obviously. Resistance I have omitted. Now if you see that the current I is dividing into the branches, now we will consider 2 loops. This is one loop, this is second loop. Okay, so one loop is A, B, D, A. So applying KVL in A, B, D, A. So A, B, D, A means this loop. Okay, this is the A, B, D, A loop, first loop. So we are going in this direction. We are coming back, and then again we are going back. So remember that whenever you are applying KVL, you need to maintain the direction. You need to maintain the direction no matter what. So in this case, we started with point A. So we are going in the direction of current. So I1 into P, I1 into P, or P into I1. Okay, P is the resistance into I1, P into I1 equals to, next is, sorry, not equals to, P into I1 plus, because we are going in the direction of current, in this case also we are going in the direction of current, so Ig into G. Now while traveling here, what is the direction? Direction is in this direction. Where we are going? Our pen is going in this direction. That means it is opposite to that. So that's why there will be minus I2Q equals to 0. Okay. Now next is applying the same thing. We will apply in this loop. BD, CB. Okay. So now we are applying the same thing on the other half. Okay. So now first we started from B point. So we are going in this direction. Current is also in this direction. So definitely it will be Ig into G. Okay. Plus this is S into I2 plus Ig. Right. Again we are going in the direction of current. This is the same direction, right? So direction of current. Now while going from here to here, current is coming in this direction, but we are going in the opposite direction. So it will be minus R into I1 minus Ig. That is the current through it. Equals to 0. No EMF is connected. So even though the EMF is connected shown in the diagram, while calculating the balanced condition, we do not need to we do not need to consider this battery at all. That is why no battery. You can see that in both cases the right hand side is 0, because the branch that we have considered, both branches does not have any direct connection to a battery, right? This branch also do not have any battery to it. This branch also do not have any battery to it. So that is why we do not have added this voltage V. So now what we have to do, we have to apply the condition of balance. Condition of balance for a Wheatstone bridge is Ig equals to 0. So if we apply that condition, Ig equals to 0, you will get Pi1 equals to Qi2 equals to 0, or Pi1 equals to Qi2, or P by Q is equal to I2 by I1. Similarly, if you apply the same thing in the equation number 2, you will get Ri1 equals to Si2, that is R by S equals to I2 by I1. So from there you get, by comparing 3 and 4, you get P by Q is equal to R by S. So this is the condition for balance in Wheatstone bridge. Now let's move on to the next derivation. that is derive an expression for force per unit length on two infinitely long thin parallel straight conductors carrying currents and hence define ampere. So here we have two thin parallel wires which is very long, obviously up to infinity. Very long means it's very long, right? And current through one of the conductor is I1, current through the second conductor is I2. Now we are trying to find the force acting between these two conductors, force per unit length for these two conductors. So how to do that? First we will assume that this wire is carrying current I, and whatever is the magnetic field due to this wire at a distance d. D is the separation between them. So that is our first step. Then we will assume that the wire is not there. This wire is kept in the magnetic field of the first wire. So then we will calculate the force acting on this. And then similarly we will assume what is the magnetic field due to this, and then we can find the force on this. So first, obviously magnetic field due to wire 1 is B1. The formula is mu naught by 2 pi I by R. Now in this case R is basically D, so mu naught by 2 pi I by I1 by D. This is the magnetic field due to the first wire and its direction. If you consider this is the direction of current, then magnetic field will be into the page of the paper. So that is why there is a cross sign given over here. Okay, so this is the first stage. Second stage is magnetic field due to now force on I2. Now next part is, this is stage 1, this is stage 2. So force on I2 is basically F is equal to Bill sine theta, but in this case as you can see the current and the direction of magnetic field, they are perpendicular to each other. Sine theta means theta is 90, sine 90 is 1. So that is why it is B1 I2 into L. So BIL is the formula. So for B we will take the magnetic field due to the first wire. For current I we will take the current in the second wire, and length we have assumed some length that is particularly for this length. This is the force, but we can extend it by applying it to the force per unit length. We will see that in a while. Now if you would add the formula for this, you will get mu naught by 2 pi I1 I2 by D into L. Now if you see that I1 and I2 are basically interchangeable, right? So even if you interchange an I1 and I2, the value should not change. Similarly, so you can write F12, this is step number 3. Force on 1 due to 2 is basically given by mu naught by 2 pi I2 into I1 by D into L. So this is the same thing, right? If you have interchange I1 and I2, the force will be from the different wire, but the magnitude does not change. So basically you can say that this is equals to F21. What is the meaning of F21? F21 is force on 2 due to 1, and F12 is force on 1 due to 2. Okay, and both are same, we assume that same value equals to some constant F. So F is basically mu naught by 2 pi I1 I2 by D into L. Now this is not over. You have to find the force per unit length, because this L was imagined by us. It was not given. The wire length of the wires were infinite, so L we assumed. So we have to find force per unit length, that is small f. So small f is basically capital F divided by L. So that is mu naught by 2 pi I1 I2 by D. So this is the force per unit length, right? And now we have to define the ampere. Okay, the term ampere. So what is ampere? If we put I1 equals to I2 equals to 1 ampere, and then D becomes 1 meter, D also 1 meter, then the force per unit length becomes 2 into 10 to the power of minus 7 Newton per meter. That is, the definition is ampere is the current when flows through each of the two parallel conductors kept at a distance of 1 meter experiences 2 into 10 to the power of minus 7 Newton per meter force. Okay, so per meter force is 2 minus 7, 2 into 10 to the power minus 7. Okay, got it. Now next derivation is derive an expression for the magnetic field at a point on the axis of a circular current loop. So here we have a circular current carrying loop, and we are trying to find the magnetic field at this point P. This is a very important derivation. Okay, Now to do that, first of all we have to consider a small element dl, okay, small element dl over here, and that dl is basically making an angle 90 degree with the direction vector. So this is our point P, right? So from the point P, if you join them, this is the line. So line, this is the line, and this is the this is in a different plane actually. That is why you cannot understand the angle theta. So this is the angle theta, which is actually equals to 90 degrees. Now the angle, the inner angle will be different. That value we are given by phi. This angle is obviously 90 degrees. If this angle is phi, the magnetic field at this point due to this small element dl will make an angle phi with the axis of the coil. Okay, so this angle is phi. Now if you derive another if you take another component which is exactly diametrically opposite, another dl component over here, okay, and try to find the magnetic field, the magnetic field will be like that. So that once you take the y components, the y component will basically cancel each other. Okay, y components will be, both values will be equal, but magnitude wise y components will cancel, only x component remains, similar to that of the equatorial plane of dipoles, right? So but we will not consider this component yet, only we will consider that only x component left. So we will only interested in the finding the dbx. We will not make it 2 dbx like we did in the equatorial plane. Okay, but we have to understand that for all such parts, so suppose you take this dl, and if you consider a diametrically opposite component dl over here, they will cancel each other. So all the y components will be cancelled, x components will left. So we are only calculating the x component, which is basically db cos theta, cos phi, y cos phi. So this is the angle phi. So x component will be the adjacent component. So adjacent component will be cos component. So db cos phi. So now we will calculate db cos phi. So what is db? From Biot-Savart's law, it is basically mu naught by 4 pi I dl sin theta by r square. Now sin theta sin 90 degree, you can write that if you want. So basically it is I dl by r square. Sin 90 is 1. Right, so it will not be having any part in this. Now dbx is db cos theta, cos phi, as I mentioned previously. So we will put the value of phi as well. So mu naught by 4 pi I dl by r square, and cos phi is, what is cos phi? If you consider this angle as phi, then obviously this is the adjacent side, that is the base, and this is the hypotenuse. Hypotenuse means it is basically r. So from here we see that you get mu naught by 4 pi IR by r cube dl. Okay, and then bx, we calculate dbx. Dbx means we have to calculate bx. To calculate bx, what we have to do? We have to find the integration for that. So integration of that will be mu naught by 4 pi IR by r cube integration of dl, because all the others are constant, only dl is varying. So integration of dl. Now what is dl? dl is a small component along the coil. So if you take all the small portion of the coil, and if you add them, you will get the perimeter of the coil. So perimeter is basically 2 pi r. So you have to apply multiply with 2 pi r. So if you see that 4 pi and 2 pi is cancelling, only 2 is left. This r are multiplying, so you get I r square by r square plus x square to the power 3 by 2. So what we have done, instead of r cube, r is what? R is square root of x square plus r square. Now square root can be written as power half. Right, square root basically power to the power half, right? So this is how we can simplify it. X square plus r square square root, that is power half. Okay, so and that is cube of that. So cube of that is basically r square plus x square to the power 3 by 2. Now there is an extra part of this question in case they ask you what is the magnetic field at the center. For at the center it will be x equals to 0. If you put x equals to 0, the expression will come out to be mu naught by 2 I by r. Okay. Now let's move on to the next derivation. This is also very important derivation. Derive Lensmaker's equation. Okay. So for that, first of all, you have to construct this diagram. Okay, and there are two mediums. One medium is N1, N2, and the third medium is also N1, right? Generally first and last medium are same for a lens. Now the refractive index of the second medium is N2. Now first we have considered the this surface. This is the first surface coming. Okay, this is the second surface. Now the radius of curvature of the first surface is say R1. So this is R1, and radius of curvature of the second surface is R2. Okay, so the radius of curvature of the second surface is R2, radius of curvature of the first surface say R1. Both can be different. Okay, they does not need to be same value. For equiconvex generally it is same, but for this derivation they can be different value as well. Okay, now when the light ray traveling from this path, suppose there is an object kept at here, the light ray traveling from O towards the lens, okay, first it encounters the first surface, okay, and then it undergoes some refraction. Once this refraction happens, it tends to move some point. Okay, say this is the image I. Okay, now for the first surface, this is the object distance and this is the image distance V dash. Okay, now for a spherical surface, we know that what is the lens equation? Remember that. Remember lens equation, 1 by V minus 1 by U equals to 1 by F. This we will keep that in mind, but we will not use this equation here. Okay, so first, what is first? First is V. So here what is V? V is V dash. And what is the refractive index of the second medium? It is happening inside the second medium, assuming entire part is second medium, right? So it is N2. So N2 divided by V dash. Very important. N2 divided by V dash minus is U. So minus U is in the first medium, that is N1. So N1 by U. Okay, equals to final medium minus initial medium divided by the radius of curvature of the surface, that is R1. Right? So this one is correct. First equation is done. Now second equation is, now the ray of light after refracting to the first surface, it now falls on the second surface, right? And again it undergoes another refraction and it reaches to the final point. This is the final point. This is intermediate image. This is the final image I. Okay. So now what is this distance? This distance is V. And this is happening in the medium N1 again. And for the incident medium, the object distance is now V dash. So this will be treated as object distance, this will be treated as image distance. Thickness of the lens is very thin because this is for a thin lens. Okay, so thickness of the lens is very thin, so we do not consider the thickness of the lens itself. Okay, but we will consider that the object distance is V dash and image distance is V2. V. And where is the object? Object is now in the second medium, right? And image is now in the first medium, that is N1. So N1 by V, that is this formula, N1 by V minus N2 by V dash equals to, what is the final medium here? Final medium is N1 and initial medium was N2. So final medium minus initial medium divided by the corresponding radius of curvature, that is R2. Okay, now we just need to add these two equations. If you add these two equations, they will cancel. So you will get N1 by V minus N1 by U equals to N2 minus N1 by R1 minus N2 minus N1 by R2. Why I have written it like this? So there was a plus sign over here, but I have made it negative sign because I have done both sides. I have done N2 minus N1. Here it was N1 minus N2. Right? It was N1 minus N2. So what I have done in both cases, I have converted into N2 minus N1 by multiplying a negative sign. Okay. Now you can take this N2 minus N1 common, on it will be R1, 1 by R1 minus 1 by R2. Now if you see on the left hand side, both has N1. So N1 will be common and you can divide it on this side. So if you divide it, it will be N2 by N1 minus N1 by N1, that is 1, equals to 1 by R1 minus 1 by R2. Again, this derivation also requires at least 2 times practice. So U is basically infinity. Not U is infinity. So now the focal length of a lens is basically defined when the object distance becomes infinity. Okay, so u is basically infinity. If the object, a ray of light is coming from a very far object, once it falls on the lens, it focused on the focus of the lens, right? That is the definition. So parallel rays coming from a very distant star actually focused on the focus of the lens, right? That is the definition, parallel rays to the principal axis. So if u becomes infinite, then the object final image will form at focus. That is the definition we are going to use here. So you will put that value over here. Okay, so v is 1 by f and u will be 1 by infinity, so it will become 1 by infinity is 0, so you will get 1 by f equals to n minus 1 into 1 by r1 minus 1 by r2. This is the lens maker's formula. Now if we consider the first medium to be air, that is n1 equals to 1, and the absolute refractive index of the second medium be n, that is the from air to the medium, then this n2 by n1 basically becomes n, right? So this is how we have arrived at this relationship. This is very, very important derivation. You have to practice at least twice, especially to remember these two equations. How you can remember? Always remember that whatever is the distance, and the same will be with the refractive index. This will be our in back of our mind, but we will not use this anywhere in this derivation. Okay, from lens maker's formula actually we derive this equation. That is why this will be only in our back of our mind, but we will not use it. Okay, so this is the derivation. So n2 by v dash minus n1 by u. So because n2 is in the second medium, v dash in the first medium, n2 is the second medium and the corresponding distance is also in the second medium. So refractive index by corresponding distance will be very, very important to remember. If you follow these steps, you will be able to solve it. Okay. Now this is another derivation. Okay. Derive the expression for the refractive index of the material of the prism in terms of angle of minimum deviation and angle of the prism. So this diagram is very, 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 very important. Okay, this diagram is very, very important, and this diagram is also compulsory. Both diagrams you have to draw. Okay, because to show that this happens only when the incident angle is equal to emergent angle. Only in that case you see that angle of minimum deviation occurs. So this is the angle of minimum deviation. This is delta m. Okay, so this is the angle of minimum deviation. Sorry, not this one. This one is the angle of minimum deviation. This is delta m, because no smaller value is possible than this, right? So this is the angle of deviation. Now after that, what you have to say from geometry, I delta, that is this delta is basically equals to I plus E minus A, and then A equals to the angle of prism A. Angle of prism A is equal to R1 plus R2. Okay, now then you can you don't need to show this geometry derivation. This is you can write directly. Okay, next is what you have to do. By observing I versus delta graph, we can see that the angle of minimum deviation occurs when the angle of incidence I is equal to angle of emergent angle. Okay, so this is the basic thing, and so basically what we can say, I is equal to E and R1 equals to R2, and that should be equals to R as well. We can write this is equals to R as well. Okay, now from there we can say that delta m, so now we have to put that values back to this equation. So delta m equals to 2I minus A, that is I equals to A plus delta m by 2, right? So just do the simple mathematics. The mathematics is simple, but you have to write a lot of things. If you miss any of them, or if you miss the diagrams, marks will not be given. So now again A was R1 plus R2. Now R1 is equal to R2 equals to R. So A becomes 2R. That is, therefore from the refractive index from the Snell's law is given by the formula n21 equals to sin I by sin R. Now sin I we have calculated I, we have calculated R. So from there you can say that basically R is A by 2. So if you do that, you will get this equation. This is the final expression. Okay, very important, very common question to is coming in your PU board exam, but lot of writing is there. It is not actually a derivation, it is more like writing practice. Now next part is from the wave optics chapter. Now we have two derivations back to back. Using Huygens principle, arrive at Snell's law of refraction or reflection, laws of reflection for a plane wave. So this is very important derivation. First of all, you have to consider two parallel rays falling on a medium line separating two medium. Okay, now when this light reached here, the light from this point only reached up to this point. That is, this is the incident wavefront. Okay, this line CA is basically incident wavefront. Now by the time the light from A reached to B, okay, light from C reached to D. Okay, now so BD is the reflected wavefront. If this is the angle of incident I, then the wavefront makes the same angle as the angle of incidence, that is I. If this is the angle of refraction R, then the refracted wavefront also makes the same angle R. Okay, so this is the basic geometry. That part you have to remember while drawing this diagram. If you draw this diagram like this, everything will be fall in place. Now wavefronts always makes 90-degree angle, so this is 90 degree, this will also be 90 degree. Okay, now what else? Next is you have to understand that the speed of light in this medium is V1, speed of light in this medium is V2. Because they are two different mediums, the speed of light will be different. Similarly, the refractive index will also be different. Okay, now what is this distance? This distance is AB. AB is basically speed of light in that medium times the time taken. So that is AB equals to V1T. Now what is the Snell's law? We remember in our Snell's law theory that Snell's law is basically talking about sin I by sin R. So from this triangle we will calculate the sin I. So sin I is basically, if this angle is I, then sin I is perpendicular by hypotenuse. This is the perpendicular, this is the hypotenuse. So from there we can say that sin I is equal to AB by CB, and AB we have already calculated V1T. Just put the value V1T by CB. Next is after that, this is the before light reaches to the second medium. Now once this light is already in the second medium. Now time for the light to reach from A to B is same as the time taken by light to reach from C to D. Right, so the time taken is basically same in both cases. So now, but the speed in this medium is different, V2. So what is the distance CD? Distance CD will be speed of light in that medium times the time. So that is V2T. So from there, triangle CBD, we can say that sin R, what is sin R? This is R, right? Sin R will be perpendicular divided by hypotenuse, that is CD by CB, that is V2T divided by CB. Now sin I by sin R is basically ratio of these two, that is V1 by V2. Now this is not the end of the derivation, this is not the Snell's law yet. Okay, so what you have to do, you have to adjust this equation, that is 1 by V2 by 1 by V1, then multiply like this, and C by V2 is basically refractive index of the second medium, and C by V1 is basically refractive index of the first medium. If you know how to do that from this step to this step directly, you can do that. Otherwise you have to be careful. V1 by V2 was there, right? That is what you can say, 1 by V2 is there, 1 by V2 into V1, right? So what is 1 by V1? 1 by V1, V1 is what? I can write V1 like this, 1 by V1, right? Same way, division of division becomes multiplication. So basically what we can say, now I take this in the numerator. So this will become 1 by V1, 1 by V2 divided by 1 by V1. That's what we have done over here. Okay, so that's what we have done over here. And if you remember it, you can answer this question easily. And then you have to multiply C on the both numerator and denominator, then you will get C by V2 equals to C by V1, that is N2 by N1. then you can just simplify it. N1 sin I equals to N2 sin R. That is the Snell's law. And let's move on. Now we will do the reflection. Reflection is slightly easier. In this case, the light again traveling here, this light is also traveling over here. By the time light reaches here, the second ray only reached up to this point, so this is the incident wavefront, and then by the time the light reaches from here to here, this light reaches here to here, so this is the reflected wavefront. Now this is the angle of incidence, this is the angle of reflection. Okay, now angle of incidence, same angle made by the plane wavefront, incident wavefront. This is the incident wavefront, so this will be the angle of incidence. This is the reflected wavefront, so this will be the angle of reflection. Okay, now in this case, light is, everything is moving only in the same plane, so speed of light will be same in both the rays. So now what is the main part? We have to prove that these two triangles are congruent. That's it. Now in case of wavefront, we know that the angles are 90 degrees, so this is a 90 degree angle, this is also 90 degree angle. Okay, wavefronts makes a 90 degree angle with the rays, right? So now time taken by the light reach from here to here is t. Similarly, time taken by light from reaching from here to here is also t. Okay, so the distance AB is Vt. AB is this distance, AB is this distance, that is Vt. Similarly, DC is this distance, DC is also Vt, right? Speed is same, time is same, so both cases it will be Vt. So basically you can say that AB equals to DC. Now we have to consider this triangle, triangle BAC and triangle BDC. AB equals to DC, already proved. BC is common, BC is common, and angle BAC equals to angle BDC equals to 90 degrees. So these two angles are 90 degrees, so they are equal. So from there we can say that by side angle side, we say that BAC is congruent to BDC. Okay, so BAC is congruent to BDC. Then we can say that angle ACB equals to angle DBC. So angle ABC equals to angle ACB. I think I made a mistake. I said DBC. Angle BAC, okay, yes. Angle BAC, angle ACB, yes. Angle ACB equals to angle DBC. Angle ACB equals to angle DBC. So that is R equals to I, or angle I equals to angle R. So angle I equals to angle R. This is the laws of reflection. Okay, so proven from the Huygens principle of theory of light. Also remember that any of these two questions will come, they will always ask state Huygens principle. So Huygens principle statement also you have to remember. We will discuss that Huygens principle in our 2 marker and 3 marker part, which will come very soon. Now next question number, now next 3 questions will be solved very easily. What is the rectifier? Explain the working of a full wave rectifier using the neat circuit diagram. Draw the input output wavefront of a rectifier. And rectifier is an electronic device that converts alternating current AC into direct current DC. And the circuit diagram looks like this. For full wave rectifier, you have to have 2 diodes, D1 and D2, and the theory is this. During the positive half cycle means when this part is positive and the below part is negative. So this part is positive, this part is negative. This is the positive half cycle. So in this case, what happens is that if you see that this diode is basically this side is positive and this side is negative. So diode conducts current, so diode D1 is open. In the negative half cycle is when this side is negative, this side is positive. In that case, you see that this diode is positive and this diode is negative. So this does not conduct, diode D2 conducts. So both cases, no matter which diode is conducting, current always flowing in this direction, X to Y direction. Okay, current is always unidirection, no matter what is the cycle, no matter which diode is conducting. So both cases diode are conducting in the same direction. So diode D1 becomes forward biased and conducts, allowing the current to flow through the load resistance RL. Diode D2 is reverse biased and does not conduct. Now you have to explain both the cycles, positive and negative half cycles. Okay, half cycle of the during the negative half cycle of the AC input voltage, the lower half of the transformer secondary winding becomes positive. Diode D2 becomes forward biased and conducts, while the diode D1 reverse biased and does not conduct. Current again flows through the load resistance RL in the same direction. So this is also very important line. Current flows in the same direction during the positive half cycle. So this is the input voltage, this is the output voltage, this is due to D1, this is due to D2, okay, and this is a fluctuating DC, not a constant DC. Constant DC generally is a straight line, which generally if you observe a constant DC, this is like a constant DC, but here we are getting a fluctuating DC, even though they are flowing in the same direction, but they are fluctuating. That is why it is called a fluctuating DC. Now next, half wave rectifier, another very important question. Most student again last year thought half wave rectifier will come, but they repeated full wave rectifier. Full wave rectifier came in year before as well as 23 as well as 24. So it might come in 25 as well, but 25 half wave rectifier is expected, but you have to prepare both of them. You cannot skip any of them. Okay, now half wave rectifier is an electronic circuit that converts alternating current AC into direct current DC by allowing current to flow only during the one half cycle of the AC input signal. The other half cycle is blocked, so only half of the AC is used. Now let's see the circuit diagram and the description. So here is the circuit diagram. In this case only one diode is connected. So only one diode is connected means when the positive half cycle goes on, so this is positive, so the diode conducts in this direction, but when this is positive, this is negative, diode does not conduct, so only half of the AC is converted into DC, remaining half is lost. Okay, so positive, but while writing it you have to mention both halves individually. You cannot skip it. During positive half cycle of the AC inputs, the diode of the anode of the diode positive with respect to the cathode, the diode becomes forward biased and conducts current. Current flows through the load resistor RL in one direction and the voltage across the load is positive. During the negative half cycle of the AC input, the anode of the diode becomes negative with respect to the cathode. The diode is reverse biased and does not conduct. No current flows through the load resistor RL and the output voltage is 0. Anode cathode means anode is basically P type, P side, and cathode is basically N side, if you are wondering. Now write the three differences between intrinsic semiconductor and extrinsic semiconductor. Draw the energy band diagrams of N type and P type temperature semiconductor for temperature greater than 0. So intrinsic and extrinsic semiconductor difference, you have to write three differences. Definition: a pure semiconductor with no impurities, a semiconductor doped with small amount of impurity to improve conductivity. Charge carriers: equal number of electrons and holes, unequal number of charge carriers in majority carriers electron in N type, holes in P type, and minority carriers. So generally extrinsic semiconductor has a majority carrier and a minority carrier, okay, based on what type of semiconductor it is, but there is no such cases in intrinsic semiconductor. Conductivity: low conductivity at room temperature, high conductivity due to doping, which increases the charge carriers. You can give one examples also, but this is sufficient. Next is the band diagram. Okay, this is an N type, this is a P type. Okay, if you see the N type diagram, there is a donor level, electrons are getting donated from this donor level. Normally the band gap is high, but this donor level sits very close to the conduction band of the atom, so that is why lot of electrons are getting supplied to the conduction band, so the band gap actually decreases. Okay, similarly for a P type semiconductor, there is an acceptor level. What is the role of this acceptor level? This acceptor level accepts electron. Okay, because of that, what happens is that there is a lot of holes created. So these holes conduct the electricity in this case, and in this case these electrons conduct the electricity. Okay, so this is the band diagram. Sometimes they might ask you explain the conductor, semiconductor and insulator in terms of band theory. That is also a less chance question, but I felt that that question may not come. Half wave and full wave rectifier are most common, and this question was given in your model paper. That's why I took this question as well. So all the important questions from these chapters are covered. You can expect at least one question from the semiconductor chapter, so don't skip the semiconductor chapter. And all the other derivations that I have done are all important. I will share the PDF. For that you have to join our WhatsApp channel, and there will be many people, they will say, I have the most probable question, I have the most important questions, I have the most important derivations. Always check the authenticity of that. Okay, there are many things that is circulated. Your career is in your hand, your future is in your hand, so don't think twice before trusting anyone. But this is well thought out, well researched derivation, so you cannot skip any of them. You have to practice them regularly, at least 2 to 3 times, and watch this video 2 to 3 times, so that you are familiar with. If you have any problem, any struggle to understand, you can check again and again. And I will be back with 2 marker and 3 marker questions very soon. So till then, bye.